meeting. So we have heard the foreign guest initiatives. So this comparison was really interesting. Now we go more in depth about what this PEPR really plans to. So today and tomorrow we have more detailed presentations about the activities in each research axis and each research project. So we start with axis 1 by chance. No, axis 1. So the one devoted to the characterization of the solar planets. So we have first sort of executive presentation of the axis for half an hour that has been prepared by the two responsibles, Nathalie Boccaletti and Claire Moutou, and Anthony will present it. And then it will be followed by a detailed description of the 5 working packages of this axis, each for about 15 minutes. Then we will have a short pause, but without drinks, we will drink afterwards, and a move to axis 3, which is more confined. So, Anthony, the floor.
Okay. Shall we start? Axis 1 is about the detection and characterization of exoplanet by direct imaging. And so I will give a brief overview of the science case and the limitation that we have today, the kind of planets that we are able to detect by direct imaging, and the perspective. So basically, what kind of development we want to push in order to make significant breakthrough in the field. So exoplanets are being discovered since the 90s, 1995 to be precise. We know about 5,500 of these exoplanets today. As you can see on the histogram, the number of planets is increasing gradually. There are some peaks which correspond to some data release of like space mission, for instance, Kepler mission, which has released a lot of detection. And this rate is still growing with more detection over time. We should expect probably another peak in very soon from now due to the Gaia satellite, for instance. And if you look to the right, this plot is showing the mass versus the date of discovery. So what is also remarkable here is that as we have many more planets detected, we also are more and more sensitive to lower mass planets, and we are now able to even detect planets that have the mass of the Earth, even below, in fact. But these Earth mass planets are not exactly Earth analog because they orbit very close to their star or different star than the Sun. So we'll see later. To study this exoplanet population, we have in hand several techniques which are shown in this diagram. Again, it's the mass here versus the separation in astronomical units, and so each color corresponds to techniques. So basically, we are covering it's log. So we are covering a lot of this diagram with the current techniques. There are more than 500 objects here, and the black ones are the planets of the solar system. And so we have two families of techniques. The one that we call the indirect techniques, which are not detecting directly the light from the planet, but only the light from the star, and infer the presence of a planet by some physical process. And this indirect detection are very efficient to detect planets very close to their star, and even further out, in fact, out to typically 10 astronomical units, and also at very low mass planets that have the mass of the Earth, like I said before. And we have another family of techniques that we call direct detection, which in that case are able to measure directly the light from the planets. But these planets are, more sensitive to these techniques. So we are more sensitive to planets that are further away in the system, more than 10 astronomical units, and for masses that are basically about a few times the mass of Jupiter. And so this part of the diagram is relatively empty, but it's not because there are no planets there. It's just because we have a detection bias. So we want to push, in fact, the detection towards this range in this parameter space. And for that we will have many more missions or instruments, especially to cover more this part of the diagram, and going down to Earth mass planet, in particular high precision spectrograph on the ground, like Espresso at the VLT or Andes at the ELT, and also space mission like Plato. This will provide many more detection. So indirect techniques are also interested not just to have a taste of the exoplanet population or the architecture of systems, but also for many of them we are able to measure at the same time the mass and the radius of the planet, so we can start to study the internal structure of these planets. And for instance, we can disentangle a rocky planet from a gaseous planet just based on the radius and mass measurement. But still it is challenging to, for instance, make a difference between what we call a super Earth, which is a heavy rocky planet, and what we call a mini Neptune, so a small gaseous planet. So we need more precision, so that's what we need space mission like Plato to refine this kind of measurement and all the follow-up on the ground with radial velocity to measure the masses very precisely. Now the main direction in the field of exoplanet is now the characterization of their atmosphere, because at some point, if we want to have some information about the habitability, we need to detect directly the light from these planets. And this is an example that was recently obtained by James Webb, the James Webb Space Telescope, on a Jupiter-like planet, which is WASP-39b, with the first detection of CO2 and SO2 in the atmosphere of this giant planet. This was the first time it was identified, this kind of molecule. And another example here that is obtained by direct imaging from the ground, it's the planet 51 b, which is a young planet with, as you can see in the spectra, the detection of methane and water vapor in the atmosphere of this giant planet. So in this field, especially in what we call transit spectroscopy, the James Webb Space Mission and also the following one, Ariel, will be really valuable to observe and to study the atmosphere of these planets. Now related to the question of the characterization of the atmosphere, there is the question of how do planets form, which is very important. And so it's not very clear yet how this planet form. There are many ideas, theories, and basically there are two main categories of that we think how the planet forms. I'm talking here just about giant planets. So the first mechanism that is considered is what we call core accretion, where we first form a solid core, like basically a super Earth, which is able at a given mass to accrete a lot of gas. But this takes quite a long time, probably a few million years, to reach a planet like Jupiter. There are also mechanisms. I have an animation here, but it's PDF, so you don't see it, which is called gravitational instability, which can occur in a disk of gas around a star. And this gravitational instability can trigger the collapse of a gaseous cloud and form a planet in a very short time scale of like probably 1 million years. No matter the mechanism which is involved in the formation of these planets, all these planets start their life very hot. In fact, they have temperature like 2,000 degrees, like 1,500, 2,000 Kelvin. And this is really interesting because a long time they will radiate energy in space, of course, so they will cool down. And what we can see in this plot, which is showing the luminosity versus the age, is that if you are able to observe a young planet, it's about 1,000 times brighter than Jupiter, so old planet. So this is very important because in terms of direct detection, it will be 1,000 times easier to detect a young planet. Planets form in disks around stars, in disks that are very complex. So their atmospheric properties will depend a lot on the disk around the star. So this disk is complex. It has a radial composition, a vertical structure. Also, it depends on the star at the center because the star will irradiate the disk. There are turbulence, etc. So a lot of mechanisms which are involved in the formation of planets. So the environment of a planet when it forms is really complex. But we have theories that are trying to for instance, to predict what would be the abundance of some elements, and in particular here we see the carbon to oxygen ratio as a function of the distance in the disk, corresponding to different positions that we call snow lines, so water line, for instance, CO2 lines, and this CTO ratio will change depending on where the planet forms in the disk, and so this information will be imprinted in the atmospheric composition of the planet. So by measuring directly the spectrum of a planet, and so studying the properties of the atmosphere, we can infer some information about the formation of the planet by this kind of abundance ratio. Now, imaging exoplanets is very challenging because we have basically to face several issues, at least two issues, which are pictured here. It's like being able to detect a candle around the lighthouse from a very far distance, like here from the lighthouses in California and the observers in Hawaii. So the first problem is the contrast between the sun and the planet, or the lighthouse and the candle, which is illustrated here, for instance, in this spectral energy distribution of a star. Here it's the sun, and the spectral energy distribution of planets in the solar system. The contrast between the star and a planet, a whole planet like in the solar system, is about a few billion in the visible and a few million in the infrared. Now, if we are lucky and if we are able to observe a very young planet, like Beta Pictoris b, for instance, this contrast is much more favorable in the range of 10 to the 4, 10 to the 5. And now for the angular separation between these two objects, the sun and the planet, we have to deal with the diffraction. And that's the big problem, in fact, that we have to face with high contrast imaging. So since a few decades, we have developed a lot of techniques for high contrast imaging, and in particular from the ground, we are limited by the turbulence that is caused by the Earth's atmosphere when a wavefront is coming through the atmosphere and reaches the telescope. And this is distorting, in fact, the wavefront, so we need to correct this wavefront to recover the limit of diffraction. And for that, we have a technique that we call adaptive optics, and this technique is involving a lot of components that you will hear about in the next talks, in particular wavefront sensor to be able to measure this deformation, a real-time computer to calculate the correction, and then a deformable mirror to implement the correction to the wavefront and to be able to recover the limit of diffraction. And then once we have the correction of this wavefront, what we want to do is to get rid of the light of the star, because we want to see very faint planet around the star. And for that, we are using techniques that are called coronagraphy, which actually was invented a long time ago at the Meudon Observatory in the 30s by Langlois. Of course, we are not exactly using the same design, but we have adapted this design to observe stars, and in particular to attenuate the diffraction. These two techniques are very important, so it's really hardware. But it's also a matter of software, in fact, because we are relying a lot on post-processing with algorithms that are evolving continuously to basically get rid of the star and be able to detect planets. So there is such an instrument that we develop in Europe that is implementing extreme adaptive optics, advanced coronagraphy, and all sort of differential imaging with appropriate post-processing techniques. This instrument is called Sphere. It's installed at the very large telescope, so it's an 8-meter telescope. Sphere was built by a European consortium in which many French laboratories were involved. In fact, French laboratories were leading also this consortium. And it will be impossible to show all the results of Sphere, of course, so I'm just focusing on two examples which I'm considering as very important, emblematic. The first one is the case of PDS-70, where we have been able to discover a planet at 20 AU from the star, inside the cavity of a protoplanetary disk. So this disk is made of gas and dust. We see here the dust. And this planet is orbiting around, and in fact it's clearly sweeping out the dust and the gas and create this cavity. So we have a direct evidence that the planet is able to, gravitationally influence the morphology of the disk. So this planet is very young. It's 5 million years or so. The age is not very precise. We have a mass between 2 and 17 mass of Jupiter. Temperature also is not very accurate. What is interesting is that, in fact, by observing with H-alpha imaging, we were able to detect a second planet, in fact, in this system, this one. And H-alpha is tracing shocks. So basically what we see here is gas accreting onto the planets and creating a shock. So we have an H-alpha emission that is visible in the optical. And this is confirmed by other results from radio interferometry, where we see here some dust which is accumulated around the planet. So there is probably a circumplanetary disk around this planet. So the bottom line here is that we are actually seeing directly a planet that is still forming. The two planets, PDS 70b and C, are still accreting gas, and they are surrounded by dust. Another example, beta peak B is a very famous system. It is seen edge-on, so we don't see here the movie, but the planet, if we observe it on several years, is moving on this straight line here, and we see the orbit here. So this is a very hot planet, 1,700 Kelvin. The distance is about 10 astronomical units, 9 astronomical units, and the mass is about 10 times the mass of Jupiter. There were also some observations with a lot of follow-up with radio velocity, which demonstrate that in the signal there is the presence of another peak, which would correspond to another planet, a second planet, beta peak C, which is closer in respect to beta peak B. And in fact, this planet was confirmed by interferometry with the instrument Gravity, which has a very precise astrometric, is able to do very precise astrometric measurements, and was able to detect beta peak C, and also delivered some spectrum of the planet C and B in the K-band, so in the near-infrared. And we do see, for instance, here in beta peak B atmosphere, the signature of carbon monoxide, which was used to, like I said at the beginning, derive the C2O ratio and have some ideas about, at least put some constraints on the formation of this planet. So this is a really interesting example where combining imaging, radio velocity, and interferometry is providing a lot of information to characterize the system. Now, Sphere is very efficient also, not only to detect planets or to observe planets, but also to detect a lot of circumstellar disks. As we can see here in this cartoon, what we see, the bottom line here is that we see a lot of structures. We see spirals, rings, gaps, shadow, all sorts of asymmetry that can be interpreted as the signpost of planets. So every time we see spiral, we think immediately about probably the presence of a planet that is generating this density wave in the disk. And so what is good here is that the instrument that we are developing to detect and characterize planets are exactly the same that we are using for characterizing disks. So disk science and exoplanet science are really going together, and they are addressed by the same kind of instrumentation. And I cannot resist to show you a few results from James Webb, because it's really recent. We have here, for instance, the first image in the mid-infrared, so it's 11 micron here, of the multi-planet HR 8799. We see 4 planets. They are really big. It's between 7 and 10 times the mass of Jupiter, and even the detection of a very inner disk, dust, that is located around the star. We can do photometry from this image and compare that to the near-infrared photometry in order to put constraint on, for instance, in that case, the radius of the planet, which was not very well constrained by the other measurements. And it was shown already by Didier before, which is a very interesting case, the planet K2-18b, which was announced recently, observed by James Webb. And so this planet would be a kind of probably a water-ocean planet. So this measurement here are consistent with the fact that there should be an ocean on this planet and a nitrogen-rich atmosphere. So this is a kind of idea of what we can do with direct imaging. Now we are, of course, limited with the current instruments. In this diagram, which is showing the mass versus separation, all these lines correspond to a statistical analysis from the sphere measurements. And we see that basically in this region where we have all the red squares, we are not very sensitive, in fact, with sphere. And all the red squares are corresponding, in fact, to prediction by evolutionary models of where the bulk of the planet population, I mean, the giant planet population should be. So, in fact, these planets are all located between 1 and 3 astronomical units, and we are not yet sensitive to this region with sphere. So we need to push all these lines in this direction. And that is basically the project Sphere Plus, which is an upgrade of Sphere, which the first objective, and it will be part of the Origins program, is to go deeper in contrast and closer to the star in order to access all these planets that are found by radial velocity, and we are not able to observe them by direct imaging, and also by Gaia. The second objective is to be able to observe very faint and red star, because this is where planets are forming in this kind of disk. So we need to understand the very moment when the planets are forming in the first million year of the lifetime of the system. And then we want to also perform better characterization of the atmosphere, and that means having some capabilities in integral field spectroscopy at medium resolution. So these are the objectives of Sphere Plus. So with this program Origin and in the Axis 1, we have decided to focus on basically 3 facilities. So the Very Large Telescope, and I already mentioned Sphere Plus as a project for the VLT, which is a kind of demonstrator. The Very Large Telescope Interferometer, there is a project named Asgard, which is an instrument to perform Nulling interferometry. Usually you combine the light from all the telescopes in a constructive manner, and here we want to build a destructive interference, in fact, to cancel the light from the star and be able to detect the planets nearby. So this is a second, basically the second facility we want to provide technologies for. And then the third one, the extremely large telescopes, which is of course a big objective in Europe, the ELT, and you can see that it's already really well advanced. In fact, it's half built at the moment. You see this very nice picture. And there will be a project, there is a project of an instrument called PCS, so Planetary Camera and Spectrograph, which is dedicated to exoplanet imaging. So PCS, the goal here is to do like a super Sphere Plus, but on a 39-meter telescope instead of an 8-meter telescope. And the purpose is to detect the reflected light of planets, and for that we need to meet very high contrast at very short separation. So we're talking about 10 to the 8 to 10 to the 9 in contrast at only 15 milliarcsecond or 100 milliarcsecond. And with this capacity, we should be able to detect and characterize about 10 Earth or super Earths and many more icy giants and gas giants. Another feature that is important in this project is the capacity to observe in the visible, and in particular at 760 nanometers to be sensitive to the oxygen line, and we know that it's a very important biosignature. So in terms of concept, PCS is really like Sphere Plus. So Sphere Plus is really a demonstrator on sky on a smaller telescope, and in particular, this is a simple drawing, but just showing that PCS is built around the concept of 2 adaptive optics in cascade. So a first one which is working at 1 kilohertz, a second one which is working at 4 kilohertz. Keep in mind this number because we will come back to that later in the different presentation. We have a coronagraph, of course, to attenuate the light of the star, and we have a spectrograph, an integral field spectrograph at medium resolution and high resolution. So the spectrograph is here, of course, to characterize the atmosphere of planet. We want to get a spectrum of the planet, but it has also an advantage in terms of detection, because the spectrograph is also used to boost the contrast, and in particular, this kind of spectrograph are meant to disentangle at high resolution the spectrum of the planet from the spectrum of the star. Of course, they are different composition, and it takes high resolution to be able to disentangle the two. So this leads to the very high goal of the PEPR Origins for the Axis 1. So we want to develop technology for high contrast imaging and interferometry with a lot of objectives in terms of gain, as you can see here, especially in terms of precision of the measurement of the wavefront, which is key to high contrast imaging. And so for the detection, we will follow the development of different adaptive optics components. So the wavefront sensor, which are measuring the deformation of the wavefront on the Earth, real-time computer, which are calculating the deformation and the correction, and deformable mirrors to implement the correction. And then we have interferometry. So more focused on VLTI with the development of integrated optics, and finally spectroscopy with the development of compact spectrographs. And I will finish with this slide. What I presented here is focused on ground-based instrumentation, but of course, if you really want to do an exhaustive study of Earth-like planets and do imaging and spectroscopy of this planet, we will have to go to space. And there are several missions that are planned, in particular this one, which is the US concept of Habitable World Observer, HWO, which is based on similar design as James Webb. So all the expertise we have now with James Webb will be very valuable for this kind of telescope. And another one, which is called LIFE, so Large Interferometer for Exoplanet, which is also studied in Europe, where it is a matter of combining the beams from four 2-meter telescopes, if I'm correct. And basically those two distributions will pursue the same idea to get a spectrum of Earth-like planet. So we are not addressing directly this mission, but in fact the technologies we are developing for ground-based telescopes will be exactly the same. Because even in space, in fact, you need to correct for the wavefront. Just to give you an idea, if you want to detect an Earth-like planet, you needed to know the wavefront at a precision of about 10 picometers. And that necessitates adaptive optics. I guess this is the same kind of problematic with interferometry, where we need to control the stability and the wavefront. And so in the next talks, you will hear about all the techniques, all the work packages that we are going to develop for this kind of application. Thank you. Thank you.
Thank you, Anthony, for this very nice and clear overview of the research axis. Are there any questions already from at this stage? Otherwise, we move to the presentation of the individual projects in the sequence that Anthony presented. So we start from work package 1.1, which is on wavefront sensors, and it will be presented by Maud Langlois.
Okay, thank you for the introduction, Anthony. So it basically set up the context, and I will be the first one to try to get you into the technological challenges. So I will present really the technological development associated to being able to optimally analyze the aberration. So Anthony mentioned from the turbulence. So these aberrations are very fast, and we need very high precision in order to get the high contrast. So this is really key in this development. And for the context, so we have already techniques that perform this. For instance, for the sphere instrument, we want to basically develop rupture technology to go a step further, and also we will have to use different telescopes. Anthony mentioned the ELT, which is a segmented telescope, so it comes with other challenges that needs to be specifically addressed. We cannot just scale up the current technology. So I will be presenting this work package on behalf of the consortium, which is a consortium including several labs, so the LESIA, de l'âme, de Kral, and the IP2Z. So IP2Z is a bit out of the astronomical scope because they specialize more in polishing optics. So we are talking about the LMR, which is a laboratory that manages high precision polishing of optical components. I will maybe skip that one. Just want to highlight that for direct detection, there is a close link to being able to control the level of aberration to very high precision. In the context of exoplanet, we don't have an infinite number of photons available. And this is also key, is you're always limited at some point by the number of photons you receive to analyze the aberration, and that's why also we want to develop new way of doing the wavefront sensing part. The goal then, as I said before, is really to push technology to be able to access very difficult detections such as the alpha sen, which is represented here, simulated from the ELT. So you see an Earth twin in Venus orbit, basically with the ELT. The previous simulation were performed for a 10-hour observation. In fact, more recent simulation will push to observing several nights and trying to combine this information to really detect this kind of target. So we are within the range shown by Anthony, where ELT would go as deep as 10 to the minus 8, 10 to the minus 9 at very large separation, and being able to capture this telluric planet and hopefully also biosignature. So we are talking about extreme adaptive optics. Extreme is just because we need a large number of controlling elements, so in deformable mirror, but also in the capacity to analyze the aberration in very fine spacing over the pupil of the telescope. So it requires many number of actuator and sensing points, so reaching a very large number also imply that we need to develop technique to do the calculation on the application of the phase deformation. So basically, adaptive optics exists, but as we scale it up to larger and larger telescope, it becomes more and more complex. So we adding a factor 20 in gain complexity, and then we really want to reach even higher precision with this increased complexity. So Anthony has shown these challenges which are actually summarized here. Also, just a reminder, so if we don't correct for the turbulence, the telescope will produce something like this, which is really not very informative. So to get the diffraction, we need to do that correction of the turbulence and on other systematics with a wavefront sensor and a deformable mirror that talk to each other and be able to counteract these effects. So I will be fast on this, but maybe I want to highlight also why I will focus on the wavefront sensor part, which is here. I show this slide because, in fact, if we want to detect this kind of exoplanet around bright stars, we need adaptive optics that require wavefront sensing, deformable mirror, and real-time calculator, as shown by Anthony. So there are 3 work packages that are closely related to each other, but there are other, in fact, in the Axis 5. We also have a post-processing technique, which is illustrated here. That's work package 5.3, and also control algorithms. So innovative control algorithm will allow to obtain the best performances by some knowledge of the physics and trying to develop algorithms specific to this, including, for instance, prediction and auto-calibration, because we're going into more and more complex. We're talking, the ALT is a very complex machine. We're talking about adaptive optics systems, which are also very complex. So there is really an advantage to benefit from the development in artificial intelligence and algorithm and post-processing to deal with this large system problem. Okay, so to summarize this work package, so I mentioned the partners. So this is the budget. Basically, we're dedicating over 7 years' time, almost 1 million on hardware, and then 750 kilo euros on manpower. So I don't like manpower. In fact, we'll be developing expertise and train young researchers, which is for me key in this technological development, because we really want to improve, we need to train these people. So these people are mostly postdocs, engineer and one PhD, in fact, who will focus on the wavefront sensor strategies. So the objective is, I mentioned, trying to create disruptive technology, optimized for this goal for exoplanet, but it will have also other output I will mention later on. So the big challenge is really operating in low photon regime, pupil segmentation, lots of systems, complex system, multiple sensors. So we also need to deal with fusion, because sometimes we don't do everything with one sensor, and we need to really use a different sensor working all together. There is the coupling with the coronagraph that Anthony mentioned, because the coronagraph is a non-linear part in the system that really see the effect of an imperfect correction, and that needs to be addressed, and coupling with also sometimes fiber, and all this in very high speed. So this is talking more than 1 kilohertz. So that needs all these sequence in measurement needs to be done at 1 kilohertz with the available amount of photons. So the project is separated in several steps. So basically, the step one is really a more theoretical and numerical development to focus on the most promising technology. So proposing innovative wavefront sensing strategies. So either completely new or adaptation of current existing technology. For instance, the pyramid wavefront sensor exists. We want to manage the non-modulating wavefront sensor in order to increase its accuracy, and in parallel, we have developed a Mach-Zehnder interferometer, which actually is used as a wavefront sensor and could also enable to reach high accuracy with low photon and high speed. So second step is really validating this technology on a bench. So here is the CRAL bench, but it will be actually expanded to test, to actually perform integration and validation for Sphere Plus as well. And then we'll do prototyping and experimental validation. This is really in order to fully characterize these wavefront sensors and making them operational before going to on-sky experiments. So here I illustrate it with the Sphere Plus experiment. In addition, we will also have some access to other telescope facility, but this is the main part in developing this Sphere Plus instrument, wavefront sensing strategy to be operational on sky. And the last step, which is quite important also for this project, we see wavefront sensing. So wavefront sensing can be related to also analyzing surfaces with nanometer precision and very fast. And this is really linked with the metrology in optics. So being able to register surfaces, optical large component or small components with high precision is really in the game for this sensor. It's really the same kind of strategy that needs to be developed. So we will also develop and validate strategy for wavefront sensing and apply to metrological application. So the step one is illustrated here. So we are used to perform simulation. This simulation become quite heavy because it reproduces what a telescope sees. It includes turbulence, many things, and then we apply adaptive optics correction on it. So this is also an illustration on the ELT-PCS, where we have some static phase aberration, and then a measure, and then the residual. If we correct, that's what we obtain, which is quite good. In addition, too systematic, we have the turbulence, which evolves very rapidly. So I said at 1 kilohertz, let's say, and then we need to do these measurements, which combine basically the systematic and the turbulence very fast. So this is an example for measurement, the residual which is after the correction, and then a second iteration. So we need to simulate all that in order to really optimize the concept. This is another example with the pyramid reference sensor on the Sphere Plus instrument. This is actually the Sphere instrument where you see you have the residual halo from the star with some issue which is related to jet stream being too fast for the adaptive optics system. If we had a second stage faster, we will clear up that zone where we actually will be more prone on detecting exoplanets. Second step is then validation on the lab. So I mentioned the CRAL bench, but also there has been an attempt to use a papyrus, and further attempt will come within the framework of this project. So this basically is a experimental part, which is in our lab directly, but which imply complex components such as a deformable mirror to correct the aberration, cameras, and so on, and the RTC, which the real-time calculator allows to send the signal that is analyzing the phase to the deformable mirror in order to compensate for the aberration. The third step, as I mentioned, we want to go on sky and prove this technology on sky, and this is also a step toward being able to build PCS, and this step is actually done by the Sphere Plus instrument, where you see an illustration here of the instrument. Basically, the wavefront sensing part is on the top part with the fast camera, and you see some simulation already performed. This system will be assembled also within the CRAL framework and with colleagues, basically to validate that the performance are at the level that we want. Another example concerning metrology, so this really illustrates wavefront sensing with the Maxander prototype we've developed, and actually a patent recently through the Pulsalis and maturation at CNRS. This is an interferometer that is actually small and easy to use, not so easy because it needs a really well-developed routine in the calibration and so on to really get exquisite results. So at the end, this was a movie. So at the end, we are in capacity to measure very fine detail at the surface of small component, which is illustrated here. This is just an influence function, so the response of one actuator from a deformable mirror. This square is 200 by 200 microns, and here we measure in step a few microns up. But at accuracy which is reaching less than 10 nanometer already. So we want to push that forward to get to the 1 nanometer regime, and this will also be applied to characterizing the deformable mirror developed in the framework of the project Axis 1 and the third work package. My last slide is also focusing on what are the applications of this kind of technology. So it's really related to either a correction of aberration in real time or high precision, high accuracy metrology in optical systems. So the first one is really manufacturing optical parts that are really precise, meaning very with high level of performances. It also includes freeform because we have a scheme in measuring things for turbulence that kind of could relate easily with the freeform optics, which is capable of simplifying complex systems, and also on metasurfaces. So for space communication with satellites, the same problem with going through the turbulence, the aberration is there, and some of this technology can definitely be used there, as well as laser communication. We can also measure waveforms from different kind of contexts, for instance, large high power laser beam, and also as illustrated here, the adaptive optics has been used for ophthalmology already, but we can envision that we can develop things more specific to that application and defense and space awareness. I think this is key this technological development, we want also to push the technology and also have a benefit to society at the end. So this is key. Thank you very much.
Thank you, Maud, for this nice presentation. We have time for a quick question. We're running a bit late, and at the same time, we can set up the Zoom call. So are there any questions for Maud? If not, pass to the next. So the next piece of this extreme optics that you have understood is the real-time computer, which is a computer devoted to analyze all the data that come from the waveform sensor and has to send signals to the deformable mirror. So the presentation and the leader of this working package is Damien Gratadour with Eric Thiebaut. Damien had to be here, but my understanding is that he got involved in an accident and ended up in a hospital as underwent surgery. Just went home. So he's giving his presentation by Zoom. And I think he deserves an applause because he's really just coming out of the hospital. So very difficult condition. Apparently the Zoom connection, unfortunately, is one way, so we will be able to hear him and his presentation. We won't be able to ask questions to him, but maybe his colleagues here in the room are able to answer some questions that are urgent ones. So, Damien, I don't know if you hear me.
I hear you. Can you hear me? Can you hear me? Yes.
At distance, we can hear you, Damien.
Okay. Maybe I can try to shout, although I have a broken shoulder, so I'm kind of in a messy state. So well, hopefully you will hear me for this presentation.
I don't know if in the room they do hear you.
Someone in the room? The room hears me. Okay, very good. So let me start right away while I'm still alive. So this is about real-time control for adaptive optics. And let me start with the usual slide about how adaptive optics works. We are trying to control in real time the shape of the incoming wavefront. What we call sensors are in fact cameras equipped with an optical device, lenslet array, pyramidal prism, etc., that encode in intensity the wavefront perturbation. We compensate for this perturbation using deformable mirrors. And the typical rate of operation of such a system is 1 kilohertz or larger. So we have to send commands to this deformable mirror using a real-time controller, realizing a pipeline with a latency below 1 millisecond. An important aspect of this is for the time to solution to solve this inverse problem to be stable enough, so we can ensure stable operations across hours of operations. And usually we measure that in terms of jitter in this time to solution, and it has to be of the order of tens of microseconds to have a usable system. So that's for the general principles. What we are trying to do in this project is to design a new brain for this adaptive optics system. We are dealing with and this was discussed by Anthony and Maud before me. We are dealing with a complex multi-physics problem. We have new wavefront sensors coming in, physical components to control that become more and more complex. So building this new brain will require multiple flavors of artificial intelligence, mixed with high performance computing as we were doing up to now. We have to handle sensors data that can come from multiple sources with significant noise that needs to be mitigated, improve linearity, merge these multiple sensors together. We want to improve the resolution of the reconstruction to control deformable mirrors with more actuator density. We want, of course, to reduce somehow the pipeline latency, enabling predictive control. We are dealing with variable conditions, so we want something self-adapting. And again, stable time to solution is key to performance, which means realizing real-time inference of whatever model-based or data-driven techniques we will be using within our new brain. Our baseline in this work package is a proven real-time controller solution, Cosmic, that has been developed initially in Paris, then in collaboration with some Australian partners, and that is already targeting a number of facility instruments. We had our first instance, well, in fact, 2 instances of the platform running as a facility on the Keck telescope. We are assembling now other solutions for the Mikado ELT project and also for Mavis on the VLT. And this is the baseline for this project. Already well integrated into the observatory ecosystem, already at scale for the most challenging dimensioning, supporting various AO flavors. And in a way, we are mitigating risk because we are using, the latest technologies available in terms of compute hardware and data transport. It's a consortium development, so the core team is in Paris, of course, but we have multiple collaborators worldwide, and it's adaptable to various workloads. So in conclusion, this platform is ready for the next level. It's scalable. We have proven that over the years, and future-proof in the sense that we are starting to integrate new AI workflows in there. Our baseline is also to rely on preliminary results of using deep neural networks to control AO systems. Most of the results I will be showing in the next 3 slides have been obtained on a realistic end-to-end simulator, and we plan to map this into an actual system on the very short term. The first example is denoising wavefront sensor data with autoencoders. This helps enhancing the limiting magnitude of the wavefront sensor. In this case, it's a Shakert-Man wavefront sensor, and by doing this, you enhance the sky coverage of your system. Things we want to, so this has been tested on a simulation across a large number of possible sky conditions. We want to extend that to the pyramid wavefront sensor, of course, which is one of the key components of the different systems we are contemplating. And we want also to work on frugality, reduce the numerical precision, reduce the footprint of an algorithm like this, and the resilience to be able to incorporate that in a system as a turnkey solution. The second example is how we enable predictive control using reinforcement learning. This has been demonstrated across different system dimensioning. Again, one of the critical aspects of using reinforcement learning is that you are basically an agent is being trained on its environment, and to train this agent, you need a reward. The ideal case, of course, is to get access to the phase variance. This works in simulation, but of course, in real life, this is what you are trying to get, so you don't have it. We have demonstrated that we can work with the residuals from residuals measurement from the system to get more or less the same accuracy in terms of reconstruction and predictive performance. I'm showing here an example of a time series where basically the reinforcement learning agent is extremely close to the direct projection of the wavefront, whereas the typical integrator solution has 1 or 2 frame delay and is behind basically what is happening in the turbulence. So again, we have demonstrated this across multiple dimensioning, up to very large scales, and we plan to again to integrate that into a real system. The last example is probably the most insightful in terms of what we actually want to do. This is multi-stage control for extreme AO, where we combine linear reconstruction, as has been done in the past decades, with nonlinear reconstruction provided by generative neural networks and reinforcement learning for predictive control. So it's really a multi-stage brain for a very complex system. It has been fully assessed on simulations, and a paper should be submitted very soon about this. But we have also been able to evaluate these kind of things on the SCEXEO bench. Unfortunately, not yet on Sky, but we know this can be integrated within a real adaptive optics bench to progress toward on-sky observations. So in terms of objectives for this project, this is separated in 2 categories. The first part is about technology breakthroughs. We need low latency, high bandwidth, and intelligent data transport. Again, our future system will gather many different sensors, will produce a lot of data in real time. We have to ingest this data at low latency, but also as intelligently as possible. So we want to put smart feature directly within data transport, and that's the first technology development. The second one is to leverage the kind of techniques I was mentioning just before, these new connectionist approaches for wavefront reconstruction, and make them as self-adapting as possible and with high resolution and sensitivity, and then merge these new approaches with classical, let's say, model-based HPC workloads into a single real-time workflow. We want to study the role of a number of new AI hardware that is appearing on the market against the GPU, that is the baseline for our solution today, with a focus on programmability, portability, and maintainability for this system, so that they can be operated for decades at reduced cost, operational cost for the observatory. The second category of objectives is to assemble demonstrators. We have 2 targets in this project. The Sphere Plus instrument that was discussed before. In this case, we are at rather high technology readiness level, and the goal is clearly to go on Sky. But we are also targeting the next generation ELT Planet Finder. This is rather low technology readiness level, and this study is really should be seen as a design enabler. We will enter the design study for this instrument while we will be producing results from this project. In terms of methodology, it's pretty simple: multi-scale and iterative co-design. We don't separate data ingestion from real-time pipeline. They have to come together. But of course, to lead this co-design study, we have to go iteratively between the two domains. And this is what is described here in the way the tasks are represented. We start from the specifications, we do the technology developments, and we end up with the demonstrator. And of course, this is phased across the next 6 years to come up first with the Sphere Plus demonstrator, and the final goal with the PCS demonstrator. And finally, this is a very collaborative framework. So we have 3 core partners in this project. Lesia at Observatoire de Paris as the project lead, involved in all work packages. CRAL in Lyon, mostly involved in upscaling self-adapting model-based machine learning methods within the real-time controller, and the lab in Bordeaux to take the lead on the low-latency data transport technology. We have also external, so non-beneficiary industry partners, Reflex CES, which is an SME in the Paris region, highly competitive in terms of new FPGA solutions. And we have also a tight collaboration with Thales Research and Technology, to be confirmed in the context of this project, but already existing in our roadmap, and mostly around frugal and real-time AI. And finally, the project, although the project will procure hardware for the demonstrator, during the development phases, we will get access to the Stream platform that is mostly funded by Région Île-de-France. It's a project from Observatoire de Paris and will be installed at IDRIS, the French supercomputing center in the Paris region. The whole platform is about €1 million project with all the newest technology available for the project. That's it for me, and here is my email contact if you have any questions.
Can you hear me? So it will be difficult to ask questions now, but really thank you very much. Buon rétablissement. So we move now to the third instrument related to extreme AO, and that's the deformable mirror. And it will be presented by Gil Moretto.
Okay, so let me talk about technology also, and I'm going to talk about the DM that's going to be used for this X number one, that is going to be used for the image exoplanet. And okay. Our rationale is that nowadays, presently, we have a serious problem with DM. If you intend to use this kind of commercial DMs if you intend to use this kind of commercial DM to imaging of exoplanets, so we have several problems with temporal bandwidth, we have a dynamic range, we have some problem with fragility, and also we have a problem of the size, and it's very highly costly. So this DM so far is not so compliant with the very challenging science case that is going to be exoplanet imaging. So the idea was to make an interdisciplinary, disruptive new technology that's going through technology innovation. And so we're going to have for this new DM three blocks of new technology. The first one is going to be the new active shape control. The second one, we're going to use a substrate of the silicon, and the silicon is not a usual silicon, it's supposed to be doped. And we're going to have extreme and nanometric wavefront metrology control that was pointed out by Langlois. So how to put this stuff off? So again, this we're gonna go with this innovation toward the Fourier compliance with the image of exoplanets. No, it doesn't work. It happens frequently with me. Okay, there you go. So for the first innovation, active shape control, we're gonna go for 3D printed electroactive polymers actuators. So this gonna give us a new kind of force actuators that's gonna be optimized to this bandwidth between 1 to 3 kilohertz. And for that, we need to develop the additive manufacturing for this kind of, this is going to be a real new technology. So we have to develop all this electronic 3D printing, and we have to develop how to print the electroactive polymers. So we had already started to do some work this month. So what you can see here, we can see a wafer of silicon, and the black spot that we can see, we printed the electronics on that. And the second technology that we're supposed to develop is going to be the silicon wafer that's going to be supposed to be doped. So we have a region here that it's going to be doped here. It's going to be a self-supported. And when we dope that area, this is going to be the first time that we're going to have an actuator that's going to be designed to act as a strain gauge. That means that's going to be able to in situ the mechanical deformation of the actuator. So this is going to be the first time. And here we can see the first printed that we are doing so far. So we printed the EAP over there on all the circuitry of this new proof of concept of DM. So we have done some tests on all these prototypes that we have developed in this first month of the project. And we can see that we can have something like the frequency, the bandwidth, it's pretty good in terms of frequency, that we have this kind of deformation for 500 hertz and this kind of deformation for 2 kilohertz. This is the direction that we're supposed to go. We're supposed to have this kind of DDM to be compliant with the image of an exoplanet. So this is our direction that we are going for. The third technology that was already pointed out by Maud is going to be this new metrology to this FlexSiMirror, to this new DM that we're going to use. So this new metrology is supposed to do the validate and the high frequency and also with a precision, nanometric precision. Also, we have the collaboration with people from Marseille that we're gonna use the phase shift interferometry to make some small EK scale characterization of this new DM. So the project was like that. So we have three partners. We have CNRS, CRAL, and the CNRS Lyon here. So we have five permanent people here. We have École des Mines at Saint-Étienne in Gardanne, and we have also Micropac, that is a national facility in France, to develop all these silicon wafers, and also we're going to develop here the ink for the additive manufacture. And also we have the INSA Lyon, that's going to develop the AAP, that's going to be the optimized AAP for this application. That's going to be our DM. So in terms of manpower, we're going to ask for at CNRS. We have two postdoc, and we have one PhD student, and INSA one postdoc, and one PhD that's going to share with INSA and with École des Mines. And the École des Mines, they have already another postdoc. So the idea of here is very work together. These people, they work here. There is a lot of interaction between École des Mines, between crowds. So we are all together here. This phase is going to be the phase of the fabrication. That means the additive manufacturing of the DM. And we're going to have also several interactions, several interface with industrial. We need help of these people here. That's even for the chemistry industry to make the EP and to make the ink for the additive manufacturing. And after we go to Coral, we go to Lyon with the help of Marseille. So we're going to integrate and test this DM. And the idea of this consortium is in 48 months to have in-lab a validation of 20 centimeters FlexSiMirror demonstrator with 1,000 actuators. So the idea is to have that in 48 months. So what is very important here is that we are working with a new block of technology for one of the most challenging science case in astronomy, that is image of exoplanet. If you can validate that for this case, we can also use this technology for several others. That's going to be much easier to do it. That's going to use this kind of DM, this kind of the active mirror to validate this new technology that we're going to need. For example, the free space, wireless communication. We have also the clean solar energy production. So they have an idea to have that space that's going to be half meters mirrors. It's going to be thousands of half meters like that. This needs to be lightweight. It needs to be very simple to do. And is where we have. We are working with additive manufacturing because if you can do one, we have the recipe to do several. And it's going to be readable and it's going to be easy to do it. This is the idea to work with additive manufacturing for this DM. And this is disruptive new technology. So we try to revolutionize this new technology and bring this kind of technology for the other application. Thank you very much.
There are questions in the room? Yeah. Thierry.
It's about your last slide, which I have a big concern with, because you're mentioning technology to have the best possible images about exoplanets, and it's something very accurate. This is astronomy, and you're talking of filling space with solar farms and things like that, which are a disaster for astronomy.
No, there's no. The idea is if we can validate this new technology for astronomy, we can use that easily for the other science applications. That is the idea. We don't need a DM, for example, for solar space farms, but we can use the same technology to print half meters. How are we going to control that? We need to use the same actuators, the same AAP, to control the shape of this. that means is active, is not adaptive. That means we don't care about the frequency. We just apply the tension if you have some problem with the shape, and the mirror is correct, and stay there. But we go for where we have the most challenging, because if you can do that, this is going to be easier. This is the idea. This is the rationale of this new technology.
Okay, thank you. So we go forward now, and we leave adaptive optics to go to interferometry. So this is the goal of work package 1.4, and it will be presented by Franz Martinez.
Thank you. If you've ever wondered about the meaning of the photonics word, it's an area of research and development that covers everything from the production, the transport, the manipulation, and eventually the detection of light at its most fundamental scale. This is obviously way too big for an area, and so our project, although called photonics, actually focuses on a very narrow application of photonics for the design of interferometric recombiners that we are going to use to contribute to the case that motivates this entire project, the discovery, characterization of extrasolar planets. Now, interferometry itself is the grandmother of all high angular resolution techniques. An infrastructure like the VLTI that you see in the background of this picture here not only features telescopes, but also an underground structure that allows to recombine the light collected simultaneously by several of these telescopes and produces an information that would be equivalent to the size of the whole mountain altogether. And you understand that at that level of resolution, exoplanetary systems like HR 8799 that we've seen in several presentations are very well resolved. And in fact, some of my colleagues are going to say that I exaggerate, but in the case of HR 8799, the planet E is so far away from its star that it's basically as simple as pointing the VLTI toward that planet alone and not being bothered at all by the light from the star. And this is where you are able to directly acquire the spectra of a planet like HR 8799e using gravity. Now, you can also deploy tricks like chronography at the scale of an infrastructure like VLTI. And this is a type of interferometry called nulling interferometry that actively seeks to cancel on-axis starlight and provides the same type of observation that you get with gravity at large angular separations, at angular separations of just a couple milliards seconds, really. And this is a mode that is going to be implemented as early as 2025 at the VLTI, and that's going to be part of the VLTI Asgard infrastructure. Now, to do this, we actually intend to deploy photonics. Now, photonics is a very specific, in this case, you have an example of device here with a 1 euro cent coin that gives you a sense of the scale of the thing that we're talking about. Photonics is a way to replace otherwise very bulky systems. You know, we're talking about recombining the light from multiple telescopes into an interferometric instrument. So here you have inputs that where you directly inject the light collected by an entire telescope, regardless of what size it makes. And you build this optical circuit that replaces otherwise very bulky and cumbersome pieces of optics. This type of technology has obvious advantages. It is very small, very compact, and we're talking about optical devices that are a couple centimeters across, really. Therefore, somewhat easy to stabilize, and feature somewhat lower operation cost because it doesn't require to cool down giant volumes of optical systems. And interferometry, in particular, is the ideal playground for that type of technology because as complicated as it may look like, interferometry only gathers a finite number of beams, less than a dozen for the infrastructures we have in mind for the coming decade. And therefore are ideal to test out the benefits of this technology. And one funny thing is that once it's designed and settled and built out of an integrated optics device like this one, the same device can be deployed at a multiple varieties of observatories, be it an actual interferometer or simply at the focus of a single telescope altogether. And so we are going to see several applications that concern VLTI as well as single telescopes. Now, why is it relevant? Because this type of technology has been used for a very long time in the area of telecom industry. And in fact, it's the very kind of technology that is used to send internet packets to your homes and laboratories via optical fibers. The reason why this technology becomes suddenly so relevant today is because of what we've heard before. We've made incredible progress in the quality of wavefront control. And now that we're able to stabilize the images of stars in something that looks like a very stable point spread function, it's no longer a fool's errand to try and couple that light into a single mode fiber that is highly selective on sky. Plus, we have two instruments that have already flown at VLTI. We have Pioneer and more recently Gravity that have convinced the community that this approach is a very powerful way to build instruments in practice. Now I'm talking about trying to look at exoplanets, and so I need to go back and refeature the properties of exoplanets that are, as we saw, very diverse in their astrophysics. But when you're designing instruments, it's good to try to translate this astrophysical information into observational constraints. And so what is relevant for this game of detection and characterization of planets is to plot them in this parameter space of angular separation and contrast, as was shown before. Now, to give you a sense of the scale that you have here, if you were to stretch your little finger at arm's length like this, and you were to try to estimate how big of an angle does your finger mask on the sky, you would be close to about 1 degree, which would be enough to cover twice the sun. It's a very bad way to build a coronagraph. It's not very good, but it gives you a good sense of scale. Now, if you divide that angular size by 3,600, you get about to this area here, and then you subdivide this into tens and tens, and here you get the unit of reference, which is called the milliarcsecond, which is a very tiny angle on the sky, but the type of angle that we operate with. The formal resolution of a telescope, like the VLT these days, 8 meters, sits somewhere about here when you're observing in the infrared. The ELT is going to be, well, 5 times this way here. And this is where you see the power of interferometry that pushes this angular resolution further toward the left, because when you look at where planets land in that plot, you see that they are mostly clustered in a corner where it's very difficult to go. They are very dark and also very close to their star, which makes sense because we're talking about objects that get further and further away on sky. Now you see that in that space, the technology that we're deploying here in the context of interferometry at the focus of a single telescope or in the context of long baseline interferometry sort of gets you closer to the left and closer in depth. And this is what I'm going to present in more details here. Now, before I get to that, I should mention that the project is the result of of intricate collaboration system. The project is hosted by Observatoire de Côte d'Azur, and the bulk of the activity is going to take place into 3 different laboratories: the Lagrange laboratory in Nice, IPAG in Grenoble, and LESIA in Paris. To these core institutes are associated 5 additional academic partners, places, and groups with whom we collaborate to deploy our instrumental concepts. And so you get KU Leuven, and the Asgard project. You get ESO, of course, as a natural partner where we deploy a lot of instruments. And you get the Subaru telescope where we also, that was mentioned before in the context of the SCEXEO instrument. We're also very happy to be able to collaborate actively with industrial partners, which was an important construction element for this project. And so we have Leti, we have Team Photonics, we have Lyonix, Bright Photonics, and also the aerospace company Thales Alenia Space that is very interested in following up and contributing to our project, funding parts of the PhD project that are ongoing. So we have 4 big work packages. I'm just going to run briefly through them. For each of these work packages, we don't start from zero. We have actual things that are already active. And here I feature a picture somewhat old of the first instrument, which is an operational fibered visible spectral interferometer that is currently operating on sky at the Subaru telescope on an instrument called SCEXEO. And it sits right here atop on the Nasmith platform of SCEXEO. And within this project here, we're going to take first and completely modernize it, deploy, explore ways of increasing the efficiency of the system, integrating a new integrated optic device that will increase the efficiency, be able to recombine more efficiently more subapertures. We are going to work on improving the injection efficiency and optimize the overall throughput of the system so we get more sensitivity. And we're going to integrate that as part of SCEXEO, the telescope, and to use this and hopefully be able to demonstrate higher differential phase calibration power. The second project concerns nulling interferometry. And here is the picture of the device that I showed earlier in the background of one of the slides, which is not a microprocessor, but an actual optical component made out of the silicon nitride. And using this particular silicon nitride that gathers in just 1 centimeter across about 14 different interferometers, we've been able to demonstrate the fact that it's possible to design complex circuits that gather functions. We've been able to demonstrate that these devices can be made active. We can, by applying electrical currents in the right places, we can actually modulate what's happening inside this thing with a 1 millisecond response time, which, as you saw, is compatible with uses on sky for real-time control and compensation of the atmosphere. Within the context of the project, we are going to actually take all of that knowledge and build a fully tunable and adaptive high contrast chrononuller device based on this. We're going to explore the capability, the uses of highly multiplex, so to replicate multiple devices on the same thing to optimize, to be able to reconstruct more interesting images in a snapshot. And we're also going to couple these with another additional component called an AWG, an arrayed waveguide, which is going to be covered in the next presentation. And we're going to use this to essentially build a very broadband nuller able to operate over as broad as a band as possible. So the technology, as you see, is clearly very mature right now because we benefit from the development in the telecommunication band, and we'll just demonstrate very advanced functionality for astronomical applications here. The third work package builds up on the amazing development made for the VLTI gravity instrument, which was a K-band photonic recombiner, which was essential to the award of the 2020 Nobel Prize Award to Reina Gensel. And here you get the heart of the recombiner is a fiber-fed chip that you see a picture of here, which is about 5 centimeters in length, and a device like so. And so we're going to build from that architecture, which is highly successful, and just build a J-band adaptation. So prepare for a VLTI able to observe at a shorter wavelength, where the resolution is actually going to be even better. And to ensure that we are able to operate in a satisfactory manner, the device is going to integrate a back-propagating laser metrology system, shooting lasers inside the photonics, reflecting through here on the primary mirror of the telescopes and then seeing its traces on the different outputs of the device so that we are sure that we control the metrology to better than a degree. And the final and fourth work package concerns the device, the design and the fabrication of a mid-infrared nullar circuitry that is going to be for the Asgard instrument that, as was mentioned before, is going to feature an nulling mode operating in the L-band. And over the course of the project, we will evaluate the potential of a particular platform, silicon germanium platform, which is a glass that has some very nice properties that make it fit to this little used L-band right now. We're going to go from the fundamental qualification of functions, such as splitters, junctions, tricouplers, MMIs, all of that between 3 and 4 microns. And we're going to use these to manufacture and qualify a complete L-band nuller that we will be able then to integrate as part of the Asgard knot nuller. We saw that our work involves a lot of industrials, and we do think that the type of thing we put forth here is going to have an impact beyond the PEPR. Within astronomy itself, we hope that the intent is, of course, to boost the importance of interferometric contribution to exoplanet science, and to generally contribute to the modernization of instrumentation. You see we have the potential to build very compact, light, stable, adaptive, efficient instruments using micro-optics. And we do think that by the time the project is over, the technology is going to be mature enough to actually fly on-board satellite, which hasn't been the case yet. And we've brought up already the EU-led LIFE initiative, which is to fly a space interferometer, for which the recombiner could very well be made out of photonics. And the US-led Habitable World Observer concept, a giant telescope, which also could feature as part of instrumentation an interferometric recombiner. But beyond astronomy, we do see ongoing developments already in the area of line-of-sight optical telecommunication. If you want to send signals from Earth to a space satellite, for example. And the fact that we here with this work are opening a new band at 3 microns where the properties of the atmosphere, which really becomes transparent, are much nicer than at shorter wavelength, makes it particularly useful. And the fact that we can integrate on-chip waveform control makes it that we can build very compact devices instead of bulky adaptive optics system. We do see a strong synergy that is not present yet in the project with another photonic component called photonic lanterns, and maybe that's going to be part of a future submission to the PEPR. And it also allows you to even think about ditching our telescopes altogether in space and build new observing instruments entirely out of discrete optical systems. And that will be the end of it. Thank you.
So we're still running late, so if there is an urgent question, it's welcome. At the same time, David Mouillet can come on stage. So the last package for Axis 1, so PCS stands for Planetary Coronagraph and Spectrograph, and so the last working package is about the development of new spectrographs, compact spectrographs. And David Mouillet is talking about that.
Thanks. Can you hear me well? Yeah, thanks. So I'm going to talk about, in this axis, about compact spectrographs. So you've heard and you have understood that for exoplanetary science there are many steps you want to go through, and from that uncorrected image, you try to correct it, to put a chronograph, and we've heard how to feed the interest signal into a fiber, monobaud fiber. And I will focus on the last stage, which is, okay, we want to characterize these informations, and which is to have some spectral information, you need some spectrograph. I will make a point about resolution. High resolution is important, both for detection and for characterization. And I will also make a point about the fact that the spectrograph you need will be completely different if you start from this stage, which is an image which I call seeing limited, defined by the turbulence, or when you are in a much favorable situations where the light is injected in a monomode fiber, as Franz has said. So here we go. Actually, coupling high contrast imaging together with high resolution spectroscopy has already been done, and this is some result from one member of the team. When coupling the best high contrast imager sphere together with an existing near-infrared high resolution spectrograph. And indeed, when you do look at the cool companion and molecular lines at low resolution, like here, you have much less information with respect to the case where you go to higher resolutions. So the level of information is much more complete at high resolutions. It will help you to get this molecular informations, physical conditions, and this content of information is very helpful also to distinguish this signature from either the noise or any perturbations due to the turbulence or optical defects. So it's very useful to have this. And the first demonstration that was obtained with this high resolution coupling demonstrate that you could have, using what you are looking for at high resolution with a match filter, you can have a correlation that tells you exactly this molecular content. So we want to do that, but because we start from the signal injected in the fiber and not from seeing limited image, the spectrograph you need is completely different. That's really a complete game changer. So currently existing spectrograph, if you want to accommodate a large telescope aperture, if you want high resolution, this is this kind of size you have, which is very heavy, very large, and all this needs to be cryogenic because you are looking in infrared. So that's really difficult, and we have these current limitations. It will be even worse if you want to go to larger telescopes, and it's getting really impractical. Now, if you are within a fiber, then the instrument will be completely independent of the feeding telescope, so you can have a much more compact spectrograph. And this is different concepts and how it could look like. It sizes from a few centimeters long for high resolutions to this kind of size, which is already demonstrated and used commonly for telecom purposes. Or this is a prototype we've built in Grenoble, which is this kind of size where you could accommodate to a similar resolution with respect to this used machine. So the point is, okay, how to do that, to mature really this kind of concepts. We want to improve the performance. We want to have an instantaneous coverage which is larger, so it will be more efficient observing with that. We want to have it more transmissive. And of course, because of the size goes also with the cost, with the ability to manufacture it, and also since it is integrated optics, then you can combine these functions and you can associate them, maybe to multiplex them, to put them in series, so you can really change the complete design of your whole instruments. So that's what we want to do. Now, we have this kind of three concepts which were illustrated. I will go through them. And this exists. This has been already demonstrated in some specific circumstances. So it does work. We do have a proof of concept. It's not just an idea. But from that stage, we want to be in a situation where we exactly know what is the ultimate performance we can get, whether it can be included in a community instrument for the large telescopes like VLT or ELTs. So the way we have to go through is, for these concepts, to really see if we can reach in practice the fundamental limits which is defined by the concepts. So we have to mature on this technological level to TRL 5.6. And what we want also is to compare in a practical manner these different solutions on a common platform, really to deduce what we can actually expect on the instruments, to define the corresponding system instruments that can be built with these technological solutions, and really to have the lessons learned how to use them in astronomy or beyond astronomy. So that's definitely essentially define our workload. I will go through this improvement we want to do for these different technologies, and the analysis we want to derive from this. First one is what is called AWG. This is a concept which is developed massively for telecommunications. So technology is quite mature for these purposes, but it's limited to these specifications, which is usually very narrowband. In telecom, you don't really care about transmission. It's focused on telecom wavelengths around 1.5 microns. So we want to enlarge this from this current maturity to what would be needed for astronomical purposes. Some work has already been done within the team and with partners and demonstrated on a telescope at Subaru. And also the question about how to use this, because it is inside photonics, to combine the different functionalities, and in particular to control the intensity in the different channels. This has already been explored also with a patent on this subject. What we want to do now is really to see how we can enlarge the bandwidth, the wavelength domain for astronomical purposes. We want also to push to see practically how much we can push the resolution, which is not a detail because the resolutions will directly drive the length of the guides inside the integrated optics. So you need to master much better all the physical constraints of your photonics components to larger size. So that's really some things we want to explore and to optimize the transmission, making sure that we do have the throughput that we need for astronomy. And of course, from that demonstrations, the idea is truly to derive what kind of functionalities, what kind of full instruments we can imagine on this basis. So that's one first step. A second step is another concept, which is another kind where we are using really the light inside a monomode fiber. This concept is really to look at an interferogram, the interference of the light within the guide, and to directly detect the intensity directly inside the guide. That means that you have the guide which is really close to the actual detector, and you have to scatter some spots on the guides in order to send part of the energy in the detector itself. This has already been used, and some commercial products exist in the visible on that concept. So here again, we are not starting from scratch. The key point in the infrared is that from technological point of view, you have to send the light on a deeper stage inside the detector. That means that a key point is some antenna scatterer that needs to be designed very carefully so that you really send exactly the amount of light exactly on the direction you want inside the detector. We are exactly in that stage now, and some prototype from the few spots has been demonstrated. Now we want to complete this stage to have a complete spectrograph. That means on longer device. And the idea is to have several thousands of resolutions over a very small range. And here again, if you master that, we want to optimize this transmission to apply this to longer wavelengths. And if you master this process, then you can think about multiplexing that and to coupling this functionality to other spectrographs to feed, to separate different wavelength channels and to integrate that into an instrument. That was a second technology. And the third one is also developed in Grenoble. Here, this is a little bit larger. The idea is to create some optical path delay of the light, which is a key point to disperse, to have some spectroscopic capability. And to combine this inside a Fari-Pro and a cross-disperser. We do have a prototype that has been tested on a telescope in Palomar Observatory in California. That's a 5-meter telescope. We do have some results. So here again, we are starting from a very good point. We want to see really how we can push the performance in terms of spectral coverage, access to the K-band, to optimize the throughput, to put as much information on a single detector. The goal would be to cover both H-band and K-band on a single detector. and to really discuss about the ultimate accuracy and stability you can obtain with this spectrograph. Once we have that, we will work in parallel on this technology, and remember, we want to derive all the lessons learned from that. We want to have a clear analysis, which is for what's needed in terms of resolution, compactness, efficiency, what is the best solution, or maybe also whether we can combine this spectrograph with first, you could think about a first stage with a low resolution dispersion, and then a second stage with much higher resolution that would be used as the cross-dispersing device. In order to compare all this, we want to have common platform on sky, real conditions, where we can compare really from the common conditions what are the different performance. We need some adaptive optics, some fiber injection, and then some sky, available sky, and the right place to do that is Observatoire de Haute-Provence, where adaptive optics already exists. We want to complete with uncompanioned fiber injection units. So we will have the flux in the fiber, and then you can feed the different spectrograph at the same time and compare exactly what kind of resolution you can get. That's what we want to do, and we want to push the performance. It will be on sky real conditions. You can see what kind of signal extraction you can optimize, and here that could be also in relation with work package 5.2 about signal extraction, where we will have really some different data we can compare. And one also point would be to see how we can optimize specific control of the adaptive optics so as to maximize the signal in the fiber and ultimately the ability we have to extract the right information after the high resolution spectrograph. As I said, this will work in parallel. The team will meet very often. We want to compare the results and to derive some conclusions about the complementarities of the different concepts. Which concept is the best for what purposes? We want also to discuss what could be some instrument designs that would benefit from different concepts, and about the applicability for astronomy or beyond astronomy. Of course, you have already heard, we have in line future projects, the ELT, and remember that the beam étendu of the ELT, when it is corrected by adaptive optics, is the same as for a small telescope. So whatever you can demonstrate and fully characterize at OHP, because it's monomode fiber, is applicable to a large telescope. The organization to do that is really reflected in the work package, which follows what I have described here. The resource budget is distributed along this scheme. Manpower is very important. We want to devote time from permanent position and to feed that with supporting postdoc, PhD, and also some engineer expertise. And we also have to notice that partnership with the people who are really experts in technology, wafer manufacturing, is very important. So the equipment and prestations which are associated to produce the wafers that we want to optimize is very important. I would like to conclude with the fact that I'm very enthusiastic with the team, where we can gather really some expertise both in relation to the technology, some scientific interests, some expertise about designing the huge instruments, and also interest to see how this could benefit from partnership beyond astronomy. That's it.
Thank you. Thank you. There is some quick question. I mean, these are quite technical talks, so it's difficult to ask questions, but I think it's important to show the level of technical complexity that this PEPR is really approaching. So, okay, then in the program there is a pause at this point, but I guess we all want to go to the cocktail, so we skip that, and we move to a presentation of Axis 3. which concerns the study of the Earth in its integrity as a planet, as a habitable planet, that will be presented by the two coordinators, so Nathalie Bolfan and Nicolas Coltice. And this axis for the moment is a single work package, but we hope that the geophysical community will mobilize more when we will have the new call for project in 2025. So I'll let you do in duo this introduction to the axis.
Let's not lose time.
Yes.
So I will start, and then I will hand on the speak to Nicolas. So. Karine, tu peux envoyer ta présentation. Ok. Tu veux le mettre maintenant, c'est ça? Bon, bref. So the idea for us, I mean, I didn't participate to the writing of this PEPR, but I was called lately to animate and motivate geologists to participate to this PEPR. So I will not be exhaustive, but I will try to convince that there is room and there is a lot of expertise in France to work on that. So the question is, how did the Earth became the Earth and not a Venus-like planet with 90% of CO2 in its atmosphere? The aim is to constrain the physics and the chemistry of the formation and evolution of our planet. And you all know why it got stable condensed water. But the most important ingredient there are other ingredients. An important one is the presence of a magnetic field, a dense, now breathable atmosphere, active tectonics, and magmatism. And we can also talk about, is it important to have a satellite like the moon for all this? So I will briefly summarize what we can do around this. But of course, it's not exhaustive, so your ideas are very important. The magnetic field is very important to shield the atmosphere and protect the surface from the cosmic rays and the solar incoming rays. So the very important question is what conditions favor the establishment of a magnetic field. And a magnetic field is created when there is liquid iron movement. So a prerequisite is that there is enough heat inside the planet to do that. So the thermal balance of the planet is very important to constrain. When did the core start to crystallize, and how did that impact the magnetic field? So this is also very important to constrain how the Earth is cooling down, and so all the data that we can gather from magneto-hydrodynamics experiments, analogical modeling experiments, and also paleomagnetism on very ancient rocks will be very useful to constrain all that. And also, so what is the recipe for core formation and what is the resulting composition that is required? So, of course, we all know that the moon forming impact is very important for building the Earth, and it will be very important to explore different scenarios. So for this, experimental petrology and high pressure and high temperature techniques will be very welcome. Mineral physics and isotope geochemistry, and also analogical and dynamic modeling. So these are techniques, and these are also expertise that exist in France, and there will also probably many things to develop. Of course, a dense atmosphere. The atmosphere is not primary. It comes mainly from degassing via volcanism. So what are the sources of terrestrial volatiles and how did they came? So this is much in relation to work package 2 that will be talked about tomorrow. How much is inherited from accretion, magma ocean crystallization, and core segregation? Are there still massive reservoirs of hydrogen inside the Earth? This is important to know. How much of it is due to biological processes, volcanic degassing or escape? So again, we will have a lot of need of isotope, trace, and noble gas geochemistry, experimental petrology, and modeling. And if I forget people, they will tell me. And maybe the most important question is when did the oceans and then life appear on our planet, and what were the environmental conditions in the Archean, what forced the oxygenation of the atmosphere, and what are the biomarkers, chemical markers, and isotopic markers of metabolic activity. And I think that geologists, and especially paleosedimentologists, working on very ancient rocks can bring a lot of expertise on this, and also with transdisciplinary approaches. So now I think I will hand on to Nico.
Thank you. So yeah, some of the questions also arise from the interaction between what is inside the planet, what is outside what is around the planet. And it is about the dynamics of the surface, tectonics. So tectonics, but also magmatism, how gases go from the inside to the outside. And there's been a lot of work on this over the past years, but we still have many questions because life probably existed before plate tectonics. So what are the types of feedbacks that we have between magmatism and tectonics and the evolution of the planet, the evolution of life? When did subduction start? And what are different regimes of convection that exist that existed on the Earth, and how they have driven the evolution of our planet? So these are questions for mostly geodynamic modelers, but also for geologists, for people who work on this interaction between the surface and the interior. So these are the questions that we ask for about when we talk about habitability as well. The Earth is also a member of a system, the planetary system. You see here all the sort of planetary bodies that we have in the solar system. And when we study the physics, the material properties, all the things that we've talked about before on Earth, the same rules apply to other planets. So we need to study the Earth also in comparison to the other planetary bodies. So these are all a lot of questions that arise when we want to discuss on how the Earth became the Earth we know today. So the PEPR is driven to make some technological innovations so that we can make some leaps forward into knowing about the origins. And there is in Axis 3, there is a new instrument, work for new instruments, and Karin will talk about it in several minutes. So it's the occasion for me to talk also about knowing the structure of the interior of the planet is very important, because maybe inside the planet also we have some remnants of the origin of the planet and how the planet has formed. So Karin, I guess she will talk about this after. So other instruments. So as Alessandro talked, there is a big challenge for the community to gather. It's yet a community of craftsmen and craftwomen. We don't have the same type of big instruments as in astronomy, so there's always some work to gather people around this. But there's been some development of instruments over the years in the community for magnetohydrodynamics, for analog modeling, but also for petrology, experimental petrology, and also analysis of microanalysis. So it's important for this community to gather and to be ready for the next call of a proposal. It's going to be our work to get ready for this. So here it's a map that Alessandro, I think, knows well. It's where the community is in France. It's larger. It's for the Programme National de Planétologie. But there is a lot of people in France with a lot of expertise that we have to gather, to put together, so that we can make a leap forward on this ground within this project. So there's not so many people here from the community, but we are going to have to work together and to find ways to gather. So we propose to have some webinars or something like that every 3 months to prepare also to work on the call of proposals, to get ready, and maybe a platform with rooms with some self-management as well, so we can work together. So this is mentioned here so that also we'll be able to discuss after if we do this or do it differently. So the challenges that we face are improving our knowledge of the Earth as a system, but through time, going back in time. And this means that we have all these disciplines to put together. Some of the challenges are that we have to, of course, make some discipline and improve the knowledge in the different disciplines, but also we have to integrate our knowledge. We have in France a community with people who make a lot of progress in their disciplines, and now this is the opportunity with PEPR to put that all together so that we can make this integration. And so we have 6 years to gather the people with Nathalie around this initiative to find some ways to also develop a new instrument for making some leap forwards in the knowledge. And it's a very unique opportunity because the study of the deep interior, of the planetary interiors, has been scattered over the years, although people are really great in what they are doing. And it's a way with PEPR to make a team again over the country. And so we hope it's going to happen. We see.
Thank you for this motivating talk, and that was very good indeed. We would like to involve the geo community more into this PEPR. I remind you that, okay, even if most of the PEPR is focused on instrument development, there is also this program, Accompagnement Scientifique, and so there you don't have to develop particular instruments in particular. So I really hope that the community of Solid Earth will participate at least massively in that program. We heard, are there questions, by the way? We heard before from Emeline Beaumont, so that in their initiative in Geneva, there is one work package in conjunction with ETH, actually led by Paul Tuckley. Mm-hmm. And so that could also be a good anchor point for international collaborations, I guess.
Yes, and there's a lot of connection between ETH and the French labs already.
Sure. All right, so then we can move to the final presentation of the day. So this single work package in this axis so far, and this concerns a possibility to deploy seismometers in the ocean floor, and will be presented by Karine Siglock. Thank you.
Merci, Alessandro. So let's see if we start in the bottom here. It's a relatively simply constructed work package. It's located at GeoAzur, which is part of the Observatoire de Côte d'Azur, and at IPG in Paris. And it combines expertise that resides in France in building the two oceanic instruments, two types of oceanic instruments, marine, geophysical, that are relevant here. So the goal is to develop new instrumentation that is autonomous and that will really be globally deployable, which is something to cover the oceans, to cover the Earth's surface, for geophysical imaging of the deepest interior. So if we go from the back here, the deepest interior is of particular interest for the origins question, because if you look at the structure of the Earth, if there's something left from the accretion and the earliest Earth, then it will be in the deepest interior. The geophysical imaging I will explain, and the emphasis here is on that we need something for the planetary scale that doesn't exist at the moment, so we're trying to make a real step change here. So the basic quest is that we want seismograms, geophysical soundings from around the globe If there's a decent-sized earthquake of the kind that happens several times every week, then its seismic waves will traverse all of the Earth. So it will go right through the middle. And if you have a seismic station deployed here, it will be recorded in the form of a time series, a seismogram. And if you are further away from the further you are away from the source, the longer it will take for the signal of this earthquake to arrive. And then you can see there are several kinds of waves. They are in these different colors that will arrive. And so these waves bring information from this interior structure of the planet. And what we're doing then is seismic tomography, so that is solving the inverse problem, asking, given that we have recorded this wave field from this earthquake on all these stations, and many, many wave fields more from other earthquakes elsewhere, again recorded on these stations, can we infer what's down here? And so a result would then be a 3D tomographic image, for example, like this one. This one shows the Pacific coast of North America. So here you see the mountains of the Cordilleras. This is the Pacific Ocean. And what's going in here is this oceanic plate that is being recycled into the mantle. So this is subduction. It's an old ocean basin that is now residing in the mantle, and it goes back to about 180 million years or so. So it's the memory of Earth history. And this is what we can see. So the question then is, so here I've been talking about a few hundreds of millions of years. That's still, far from being earliest Earth information, which is what we're interested in here. And so the question is, where do we look for that? And so if you look at this, this is an artist's rendering, right, of the dynamic nature of our planet. So what do we have here? For example, this is a subducting plate. As I just showed you, it goes down here. And it goes down until it gets to the boundary between the mantle. This is all this rocky, so this is rock, it's solid, to the Earth's core, which is largely iron, and it is molten up to here. Here it has a magnetic field developing, and here this is also iron, but it's already crystallized. And so this is one form of turnover, of convection, that is constantly mixing up the mantle. Here's another one that's a rising plume, which makes sure that the mantle is very well mixed. So in this area, we won't see anything of the really old structure. Maybe geochemical traces, but nothing structural. The core is fluid, so this is completely mixed, so we won't directly see anything here. Maybe the inner core, but it's not as old as the Earth. But it's solid. But then the place to look is this huge density interface between the relatively light rocky mantle and the very dense core. So the core mantle boundary would be the prime imaging target, for example, in a context here. And that's what a current seismotomographic image looks like of the core mantle boundary. So the blues here means it's where seismic waves propagate faster than average, and red is where they propagate slower. And you can see some large-scale patterns. For example, tends to be this band of upwellings, of hotter parts. Presumably the core is losing its heat in the southern hemisphere. And for example, there's a suspicion that these might be really ancient signatures. Right, those would be our best targets for thinking that's the really old Earth history. And so we would like to get really sharp pictures of this, because currently we don't really know what this represents. We just don't know. But the problem for the imaging is that the Earth, with its seismic sources, which are equivalent to electromagnetic sources for sounding space, for example, they are not distributed at all the way we would distribute them if we could. So these earthquakes, they are green. They are always in the same places along plate boundaries, and we will never change anything on that. So we will always just have our image, our light sources, so to speak, along these plate boundaries. Now that's already a big limitation. But then add to this is the red. Those are our sensors. And so they are seismometers, and almost all of them are on land. It's relatively straightforward to put seismometers on land, but it's very difficult to put them in the oceans. And the few that are in the oceans, just a few % of the total, are on the oceanic islands. So you can imagine that, because what we need is wave paths that go from earthquakes to sensors, and they should cover the interior very evenly, but this is extremely uneven coverage, and that strongly limits our resolution, especially in the deeper parts of the interior. So for example, in this case, this is how the core mantle boundary against this deepest part of the mantle is sampled by the waves that are most relevant, because most highly resolving. And you can see where we have red areas, there the core mantle boundary is quite well sampled. And then we have these huge gaps where there's almost nothing. And so this is the challenge that we want to address. And for this, we need to somehow fill these huge gaps in the oceans, which make up 2/3 of the planet's surface. So we do know how to instrument the oceans. This is an ocean bottom seismometer, which is just coming back from a 1-year deployment. So it was sitting on the seafloor. In fact, this is the sensor. It recorded the vibrations sitting on the seafloor of the Earth, the earthquakes, and this is the electronics and the flotation. And you can see getting it back, it's quite a big instrument, and what's worse, you need a big research ship. And you need that research ship to recover the instrument, but you needed another big research ship 1 year earlier. And that is incredibly limiting. So that we don't have these research ships. Also, they are very expensive. They're polluting, increasingly a concern. So we just won't scale this technology. But it does deliver very nice data via these seafloor instruments. So at GeoAzur, we've been pursuing another approach, which is more resource efficient in avoiding the research ships, in avoiding the research ships. So they are autonomous floats that don't sit on the seafloor. Ideally, they would, but they don't, because that lets us make them very, research efficient. They look like this. They're quite compact. They can be deployed by 1 or 2 sailors. You don't need a big ship. And very crucially, you do not need to recover them. So you don't need a second ship to get them back, because they periodically come up to the surface and send their data back. So that means you don't need the physical device back. They have a long life and they drift passively in the oceans. That also means they're not always in the same place. Over time, they cover all of the oceans, which is what we want. So these have been named Mermaid Float. So they're independent divers. Their work cycle is you have to go put them in the ocean somewhere. So you need some kind of ship, a small ship or a research ship, whatever you have, a piggyback experiment. It dives down to about 1,500 meters depth, and it listens if it can detect an earthquake. An earthquake waves runs along the solid earth, but it also always couples into the water column as an acoustic wave, and so a decent-sized earthquake will be heard by this mermaid carrying a hydrophone. It will decide, oh, this is a sufficiently interesting earthquake. I go up to the surface, I send it to the Iridium satellite, the satellite sends it home to our lab, and then the mermaid goes back into its listening position and keeps drifting until it hears the next earthquake. So this idea has been conceived of by Hugues Nollet, who's actually here and realized at GeoAzur mainly with Chief Engineer Jan Hello, and has been operating very reliably for more than 5 years now. This is the current fleet of mermaids that are in a very remote part of the South Pacific and have been sampling this area for more than 5 years, sending back their data with really excellent reliability. And the inspiration for this was the Physical Oceanographers Argo fleet. So they have by now 4,000 of these floats, not hydrophones, which are more difficult to run. They measure temperature and salinity, and from that they calculate the ocean currents and have had a huge impact on climate studies in this. So this is what we'd like, and you can see there is a precedent for that. It is a scalable technology. You've all seen slides of what other uses are for these technologies to be developed in the PEPR, and I'm just going to talk about this first. So if the mermaids, as they are already becoming environmental platforms for sounding the oceans. There is no other acoustic platform really to listen what's going on in the oceans, and so these mermaids, besides hearing earthquakes, they also hear whales, for example, ship noise or man-made noise, which is of increasing interest and concern, weather, which is surprisingly little other measurements. And you could imagine anything else that goes on in the oceans. And this is also going to be true for this development that I'm talking about, the bouncing ocean bottom seismometers. Ask me if you want more details. I just won't have that much time. So these drifting mermaids have been a great success, but they have some serious limitations, which for structural imaging of the kind of the fundamental science that we want to do here, and so it's great that we can address this in the funding scheme of this PEPR. And the main problem is they are only hydrophones, so they record only acoustic waves, which is not the same as sitting on the seafloor coupled to the solid earth, which is a seismic wave. It's a solid earth wave, and it has more aspects and more components, and specifically it doesn't record shear waves, which are very important for the deep earth imaging and for answering these questions about structures in the deepest mantle. And so that is something that will be remedied by this step change in the technology. And so this is about merging the strengths of the mermaid floats and the real seismometers that sit in the ocean. So, okay, if it is a real seismic sensor, it will sit on the seafloor and is coupled to the seafloor. And the disadvantage, as we said, is the ship has to come, put it down there, come back after a year, get it back up. Sometimes that doesn't work, and then everything is lost. The mermaid has the advantage that it's cheap and you don't need ships much, and they send their data back. So this advantage we absolutely need to retain. And so the BOPS, the bouncing ocean bottom seismometer that we have conceived of, will be like a mermaid, still relatively light, but it will have a real seismic sensor. It will dive deeper than the current mermaids and be able to sit on the seafloor, and the sensor will be coupled to the seafloor and record real seismic waves, the earthquakes as real seismic waves. Occasionally it will come up and send its data, maybe not quite as often as a mermaid, and will go down again. So it's really the fusion of these two kinds of technologies, which we are really well positioned to do, because GeoAzure is currently the only lab pursuing this strategy worldwide, basically. Okay, so the key new thing then is that it will be mechanically coupled to the seafloor. It will still not require a recovery. And so we want to build a performant and readily scalable technology for seismology, geophysics on the global scale. And so a few more, just what will be the sub-work packages, or what will we actually do. This is here what a current mermaid float looks like, and you can see into the interior. It has here its components. And so these have been developed by GeoAzure, and they are manufactured in partnership with a small enterprise, an engineering firm of about 15 people that's located near Toulon, called Océan. Okay, so this is a mermaid. The first thing we will need to do is upgrade the hydraulic unit. So the way the mermaid goes up and down is it changes its density. How does it do that? It takes oil that is here in this internal reservoir and pumps it out into this external bladder. So now its volume is bigger with the same mass as before, and so it's more buoyant, and this is how it comes up. So this hydraulic pump needs to be upgraded, because to sit on the seafloor, you need to routinely go to 6,000 meter water depth, which is quite challenging, and so this is not a routine step necessarily, and also the oceanographic floats cannot do this at the moment. The biggest challenge is going to be the coupling to the seafloor. So we will need to add a component that's not at all here yet. It will be an anchor or a weight, and also a seismic sensor. And that's the question, how to do that. The cartoons that I showed of putting something next to the mermaid is probably not what we will do. So we're considering this at the moment, but most likely the actual seismic sensor will need to be integrated, will be part of the anchor. Because it doesn't need to land and couple only once. It has to go up again and go down again, go up again. So this is a challenge that nobody has faced before. And I think it's the most ambitious part of this PEPR work. Finally, because all this takes more batteries, both the seismic sensor takes more batteries, and going deeper takes more batteries for the hydraulic unit. So we're going to look into extending the battery life by harvesting renewable energy. And there are two possibilities for this. It would be either solar energy while you stay at the surface to recharge your batteries, or you harvest heat, basically energy, from the thermocline, the top layer of the ocean, where the temperature quickly goes from surface temperature to very cold, close to 0 degrees. And finally, we want to be able to talk more with the mermaid during its mission, so a more flexible back and forth communication and reprogramming as needed. And that will be the final work step. Thanks.
Thank you, Karin, for this very clear presentation. Are there questions in the room? Yes. Two.
Just one curiosity. Having worked with an InSight mission, one of the problems we had was the noise given by wind on the cable. I'm not familiar with the current in the deep sea floor, but what about tethers or cable for pass the signal from the seismometer to the electronics, and how currents can give noise on the signal?
Well, the challenge, the noise will come from imperfect coupling of the sensor to the seafloor, so that the deep ocean currents are pushing the sensor around. The cable connection is not an issue. That's not the limitation.
Yes, a quick question. How well do we know the nature of the deep sea floor? We've seen images of the Titanic, for instance. It seems that it is very soft in a way, yes. Just like dust settling, in which case it will not bounce. I mean, the waves will not propagate. Yes. And on the other hand, we have probably places where you have a lot of structure, on the contrary, rocks and fissures and things like that. So how could you deal with that?
You're right, it's very variable. In some places there are lots of sediments. Other places by nature, like a fresh spreading ridge, has 0 sediments, can be very rough. This is a problem that is faced by ocean bottom seismometers since always. So sometimes you're simply unlucky and you dump it in a place, because you just throw it overboard, and this is the same. That it sits in a place where it doesn't deliver good data. Now this will be mitigated here, that because it comes up periodically, and when it says, oh well, when we see that this is not a good spot, then we just tell it to stay in the water column. It'll behave like a mermaid for a while, drift away, and sit down again elsewhere.
Okay, thank you. One more? Yes.
Sorry, it's completely out of my competence, but is this mermaids, I don't know how many you are going to have, but is it not a very good way to detect submarines, to map oil shores and all this kind of thing, which are nothing to do with fundamental research, actually? So yeah. Do you face this problem? Because I would be surprised that, for example, the Navy, or French Navy, or American Navy, would not be interested by such a thing.
So far, this hasn't been much of an issue for seismology, because the seismic frequencies are lower than the frequencies, that ocean acoustics that the Navy also would be most concerned about. That's the audible frequencies. For us, seismology plays out mostly below 1 hertz. So they're not so worried about that, and so that's why, ocean bottom seismometers who don't raise a concern. So I don't think this will be an issue.
Yeah, but remember, our instruments want to be used also in applied science. So this is one of the goals of the PEPR. So this is one of the most clear cases of instruments that can be used in a variety of ways.
So to add to your question, I mean, the current incarnation of the Mermaid, we're in the process of upgrading, so it carries a second hydrophone at the acoustic frequencies, so that you hear almost all the whales which sing at very different frequencies, or chant at very different frequencies, the rain. And so we will have a higher frequency hydrophone, and so if we run into trouble with the Navy, we'll probably soon know, and we can give an update.
All right, so it's 7 p.m. sharp, so right on time for the well-deserved cocktail. That's very good. Before we go there, let me remind you that tomorrow we start much earlier at 9. It will also be a long day, but we'll try to keep this kickoff confined in 3 days. And wow, the good news is that because there are not too many people left, we probably can drink more.